and welcome to a video on the extreme value theorems and extreme values. In this video we're going to determine the local or global extreme values of a function. We're going to talk about the extreme value theorem, and we're going to just talk conceptually about how and when an extreme value can exist. So to do that, let's look at an example, y equals x squared, and this is a function you should know pretty well by heart that looks like this. Now if you look at this function, it does not have any maximum values because the end behavior is that as you go to the left, your function increases to positive infinity, and as you go to the right, the function increases to positive infinity. And infinity is not a value, therefore there are no maximum values. However, this function does have a minimum. Its minimum here is 0 because as we approach the vertex of the parabola, we get a minimum value. So if we think about limiting the domain a little bit for this function, so let's think about what would happen if we make the domain be from 0 open to 2 closed. If we're going from 0 to 2, this point would be 2, 4. This point, of course, is 0, 0. Now, if we look at this function, there is no minimum. And the reason for that is that we can get infinitely closer and closer and closer to that 0 value, but we never stop. We just continue getting closer and closer. So we never actually reach a finite number that is the minimum value. However, because it's closed on the right side of the interval, we do reach a finite value when we get to the maximum. So this has a maximum of 4 at x equals 2. The maximum value is the y value. Where it happens is the x value. So pay attention to that vocabulary. It's very important. The maximum is the y value, and where it happens is the x value. Let's think about what would happen if we went from, let's say, -2 to +1, both open. So in this case, we're going to modify our picture a little bit here, and we've redrawn our picture with our new values. For this problem, we want to look and see if we have any maximums or minimums. So if you look at this, our minimum value occurs here at 0, 0, so we do have a minimum of 0 at x equals 0. We don't, however, have a maximum. Now, if we were looking for a global maximum, we would want the maximum value, which would possibly happen here. But because that interval is open, we don't have a maximum value because we could continue getting closer and closer and closer to the y value of 4, but never actually reach it. So we don't have a maximum here. Neither do we have a local maximum here. So this might be a local maximum because it's the most maximum value within a certain domain near that point. However, we have the same problem with this point. As x gets closer and closer and closer to 1, the y value continues getting closer to 1 but never actually reaches it. Therefore, there is no maximum. So for this problem, there is no maximum, but we do have the minimum of 0 at x equals 0. So let's go ahead and look at the extreme value theorem now that we kind of have the understanding of the open and closed intervals. The extreme value theorem says that if f is continuous on a closed interval, then f has both a maximum value and a minimum value. Now the most important part about this statement is the closed interval. This is what allows us to have a max and a minimum, and this is very important also. The function has to be continuous. So let's just think about what that means. If I have a function and both endpoints are closed, let's say it goes like this, it must have a maximum and a minimum on that closed interval. So if we look at this, this would be our global maximum value. This would be a local minimum value. This would be a global or extreme minimum value. This would be a local, and this would be a local. So this is a local min, this is a global min, this is a local max, this is a global max, and this is a local min. It's important to always consider endpoints when you're doing these problems. So let's look at an actual example and see how to apply this. So here's the problem. Let's find the absolute maximum and minimum values of the function f of x equals x to the 2/3 power on the interval from -2 to 3. Before we actually find the absolute max and min, we want to determine if it has a max and min, or if it has to have a max and min. And so we look at the extreme value theorem and we see if it fits the conditions of the extreme value theorem. First of all, what are the domain restrictions, if any, of this function? So our domain for this function would be that we don't have any restrictions, because this function is the same as the cubed root of x squared, so we can put in any value that we want for x. So our domain is all reals. So that's good. That means this is a continuous function on this interval, and this interval is closed. Therefore, the endpoints may serve as maximum and minimum values. So what this is saying is this fits the conditions for the extreme value theorem, which means this function must have both maximum and minimum value on that closed interval. So now our job is to find it. So in order to find the max and min, we can look at the graph, and it is kind of nice to look at the graph. So here's the graph of this function, and we're looking at it from -2 to +3. So you can clearly see that there's a maximum here, but there's also a maximum here at this endpoint, and this maximum is higher. So this would be the global maximum. This would be the local maximum, and then we have this minimum value right here. So if we look at this graphically, we can see exactly what the maxes and minimums are, but let's do this analytically so we have something to look at in terms of the calculus we're going to use to solve this problem. The derivative is what we want to use. So where the derivative equals 0 or does not exist are our critical points. We want to find our critical points. So we've got 2/3 x to the -1/3 power, which simplifies to 2 over 3 cubed roots of x. Now if we look at this, we have a domain restriction of x cannot equal 0, but that is only a domain restriction for the derivative. What that means is this function is not differentiable at x equals 0. However, the function does exist at x equals 0, therefore there could be a max or min. So we have a critical point at x equals 0 because that is where f prime does not exist. So we're looking for these critical points. We're looking for where the derivative does not exist or equals 0. Now that we know that that's a critical point, we need to check our function at the endpoints and at the critical points. So we need to calculate f of -2, f of 3, these are our endpoints, and we also need to check f of 0 because that was our critical point. So we're going to calculate these three values. When I calculate f of -2, I get 1.587. When I calculate f of 3, I get 2.08. When I calculate f of 0, I get 0. Now we can clearly see that this is a maximum and that this is a minimum, but because this is in between, we don't really know what's going on there. Okay, here's another thing we can do with our sign chart, SIGN. Our derivative is going to go from -2 to 3, and we know we have a critical point of 0 in here where the first derivative does not exist. We know that at -2 we have something going on. We're not sure if that's a max or min. We know this is a max. We know that this is a min. So we know that our function is doing this. So a good assumption would be to see if our function is doing this, and perhaps this is a maximum at -2. So let's check our derivative in this interval in between -2 and 0. A good checkpoint would be -1. So if we calculate the derivative f prime at -1, do we get a positive or a negative value? So we're going to do 2 over 3 cubed roots of -1, and that is going to be a negative value. So we know our slope is going downward because our first derivative is negative. So we have a maximum at 2, a minimum at 0, and a maximum at 3. So a sign chart is a really nice way to check to see what's going on. But remember, you need to check your values and always check your endpoints.